guys. So what I'm going to do today is work on the last related rates example and one of the Turvey problems. I'll help you set that up. So sorry for the weird screen setup, but it's going to end up working out. I just want to be able to show you all of this. So let me start with this first example. I'm going to do example 9. So find it in your notes. I'm going to slide it here. I'm not going to zoom into it, but this is the example. They talk about a revolving beacon in a lighthouse, and this one's a little bit complicated because they do everything in revolutions per second. So that'll be our units for part of that. And basically, I'll read the question as I set up the problem. So watch my work here. So they start with a revolving beacon in a lighthouse. Makes 1 revolution every 15 seconds. So excuse my drawing, but let's call this right there our lighthouse. And it's going to go this way where here's the beach. So this will be the beach over here. And they say the beacon makes 1 revolution every 15 seconds. So because we need to make this a special shape and we have to try to make this problem like we make all of our related rates problems fit a formula, I'm going to make this a right triangle like that. And I'm going to call this diagonal line here, the hypotenuse, I'm going to call that my beacon. And so what that means is this line is going to go all the way down the shoreline. So starting at the beginning, once again, it says that the beacon in a lighthouse makes 1 revolution every 15 seconds. So that's 1 revolution for every 15 seconds. The beacon is 200 feet from the nearest point P on a straight shoreline. So here's the nearest point P. Here's the straight shoreline. And right here, that's going to be the 200. They want you to find the rate at which the ray from the light, so here's the ray from the light, moves along the straight shoreline when you're at a point 400 feet from P. So when it's right there, and this side of the triangle is 400, I want to know how fast this is moving. So if I start labeling everything, I have that I'm going to call this distance y, this distance x, so that x is 200. This thing is not going to move out of the ocean towards the beach. So I can say that dx dt is 0. That's not going to change. My y is 400 and dy dt is what I'm looking for. Now the only thing I'm missing here is that diagonal. Now here's the tricky part. It says that you're moving in revolutions per minute, so, or second rather, 1 revolution every 15 seconds. So what I want to do is convert that. I'm going to convert it into units we know from pre-calc. If I talk about the angle in this problem, that's why this one's tricky, that's why I made you a video. The angle in this problem as the angle theta, then I can talk about things as in terms of revolutions. Revolutions we deal with angles. So I'm going to convert this into 2 pi, which is 1 revolution every 15 seconds. And that I can relate to this angle right here, which means I now have a d theta over dt. So now what I need to do is make a relationship between the angle, since that's the information they gave me. Revolutions means I'm going to work with angles. A relationship between this angle and the sides that I have for this particular triangle. So again, what's happening is here's our lighthouse. This is the beam of light coming out from the lighthouse. It's going to travel this way, so this diagonal will change in its length. I will have to label it as a variable h. And what I'm going to do is now come up with a relationship between the things I know and the things I'm looking for. So I'm going to work with, since I have the opposite side and the hypotenuse compared to this angle theta, I'm going to go ahead and work with the tangent. So that would mean the tangent of the angle that's created from the light beam to this side is the tangent of theta equal to the opposite side, y, over the the adjacent side, x. Now to make my life easier, because once I set up a relationship, I'll take a derivative, is I'm going to go ahead and move this x over to the other side. So I'm going to move this up here by cross multiplying, and I'll get x times the tangent of theta equals y. So again, what I did, and I know it's hard to see because I'm right-handed, but what I did was I moved this up here. Now I'm ready to take a derivative. So I'm going to have to use the product rule on this side right here. So that'll be the first function, x, times the derivative of tangent, which is the secant squared of the angle. Now because we're doing, again, related rates, if I do that derivative, I need a d theta dt plus the second function, tangent of theta, times the derivative of the first function, x, which is 1 dx over dt equals the derivative of y now will be dy over dt. Now once you go ahead and take your derivative, you can start substituting in values. Well, we know x is 200. That's from right up here. Well, now the secant of theta, that's going to be tricky. I'm going to have to figure that out. I'll show you that in a second. But the secant squared of theta, I'll find out the secant and square it in a few minutes. D theta dt is given up here. That'll be 2 pi over 15 plus. Now the tangent of theta I could figure out. Now we have numbers. Tangent is opposite over adjacent, so that will be 400 over 200. Dx dt we know is 0. That will cancel that whole term in a second. Equals the thing we're looking for, dy dt. So now I have to talk about finding this tricky secant. Now remember, we know all of our trig functions and we have a right angle triangle. So what I could do is use SOHCAHTOA and secant is the reciprocal of cosine. So that means I need the hypotenuse divided by the adjacent side. Now the adjacent side of our angle here is 200. All I need now is the hypotenuse. Again, secant is hypotenuse over adjacent. It is the reciprocal of cosine. So again, I'm going to do the hypotenuse first, divided by the adjacent, so I'll need to find that hypotenuse. So I'm going to do some scrap work over on the side here. So my scrap work, separate it. My scrap work is going to give me that hypotenuse. So using the Pythagorean theorem, where x squared plus y squared equals our hypotenuse squared, I'll fill in the 200 and the 400. So I filled in x is 200, y is 400, and then I simplified this and made it all nice. You can check this on your calculator, but you get 200 radical 5. Now again, I'm going to leave it like that because I want to show you some cool simplifying that happens over here. We still always need to be working on our algebra. So I'm going to go ahead and plug this in over here as my hypotenuse. So that'll be 200 over the square root of 5. And again, if you simplify all of this by hand and take a square root and leave it as a radical, this will work out to this nice number. So now, over here, simplifying all of this to finally get dy dt, this term cancels out because 0 times anything is 0. And then watch the cool thing that happens over here if you didn't get a decimal. The 200s cancel out because they're a form of 1. So I have the original 200 in the front of the problem, and now I'm left with the square root of 5 squared. Well, the square root of 5 squared is just going to be 5. See how cool that worked out? Now I still have my 2 pi divided by 15, and that will be all equal to dy dt. Now all I have to do to simplify this is multiply everything together. So I'm just going to multiply the top numbers together, and I get that dy over dt equals, it ends up being 2,000 pi over 15. And since we're measuring this side of the triangle, and that's 400 feet, and this was in seconds, this would be our units of feet per second. Now again, this one was a little bit tricky because up here, here's our beacon. We have to talk about how that ray coming out of the lighthouse, that ray of light, is going to move along the beach. And they gave me revolutions. That was my key to use trig per second. I turned that into something that dealt with angles. So we always work in radians when we're in calculus. The next part of this video is going to be the Turvey example from the homework problems. All right, this next example is going to show you how to set up the picture for Turvey's number 3 and 4. So here's your Turvey. We're going to do numbers 3 and 4, and it deals with a baseball diamond. Again, I know it's hard to see because I'm so zoomed out, but let's look at the work while we read through the problem. In this one, they give you a baseball diamond, and they said a baseball diamond is a square of 90 feet per side. So I went ahead and drew myself a diamond here, home, first, second, third, and I labeled these two sides 90, but remember it's a square, so those two sides are 90 also. Now I have our beloved Coach Frank running from first base to second base. So that means he's traveling in that direction. And they say he does that at 25 feet per second. So I need to label that side. I'm just going to call this side X and this side Y. And when he moves from first to second, that means my dy dt is going to be equal to 25 feet per second. They want to know how fast he is moving away from home plate when he is 30 feet from first base. So that means the distance between Coach Frank and home plate is the dotted line here, and I'm going to call that side Z. Because it's a square, at first base there's a right angle. So I have a right angle triangle here where x squared plus y squared equals z squared. And we've done some examples like that in class. So what I'm going to do now is finish labeling everything. They say again they want to know how fast the distance from home plate to Coach Frank is changing. That's what they mean by how fast is he moving away from home plate. They basically want us to find dz dt when Coach Frank is 30 feet from first base, which means when y equals 30. Now we'd have to figure out z, so we'll solve for that using the Pythagorean theorem. X is not going to change. That's going to be the distance from home to first. That will be 90. And again, since it's not going to change, dx over dt will be 0. So you have y and dy dt, x and dx dt. You're looking for dz dt, so the last thing we'll have to do is find z. And then you can go ahead and take your derivative implicitly. So you'll go ahead and plug in the 90 and the 30 into the Pythagorean theorem, and you'll be able to solve for z. So you guys can do that. You'll have 90 squared plus 30 squared equals z squared. Solve that and you'll have everything you need to take your derivative implicitly. Now in number 4, you're going to use the same information. So whatever you need from problem 3, they want to know the exact same thing, except you're going to change your values because now Coach Frank is 45 feet from first base. So your triangle, let me actually draw the whole baseball diamond here. Home, 1, 2, 3. Now your X is 90. He's farther down, so this is 45, and they still want to know dz dt. So you're just going to make your dy dt the same information as the first part, 25, except now y is 30, your x is still 90, your dx over dt is still 0. You'll have to find your new z, and then dz dt is what you're seeking for. So if I separate them for you so you can see, these two problems have the same setup, except the only thing that's changing is that y is 30, and I wrote 30 down here. Y is actually 45, so that matches that. And from there, you should be able to set everything else up. Use the Pythagorean theorem again down here to find z, and then using your derivatives implicitly, you can find dz dt. I'll see you guys in class on Monday.